Let's take a look at this figure. So it's a simply supported beam, so not a big deal. The supports and the force are given to us in the problem statement. The value for the force is right on top. It says 12 KIP. What is KIP? It's kilopounds, right? So the section is at the bottom. So there are 2 points that belong to the section which are of interest to us, and we would like to calculate the stresses for those points. We're going to get there in just a little bit, but before we do that, there are some basic statics calculations. There are some basic statics calculations that you need to be able to take care of, right? Before we get to the strength of materials part of the exam. And that's always true. I'm sorry, I mean, but this is what strength of materials is, right? So we solve the problems with statics first, and then we're gonna do some more calculations to get the results which pertain to the strength of materials. Yes, this class talks about the stresses and the strains and those calculations, but if you cannot calculate the forces, the internal forces in a section, then you won't be able to calculate the stresses and the strains. That's why statics is a prereq for this course. So this is just a quick reminder. I'm not trying to be critical of anyone. I'm just telling you this is how the course has been structured. That's all, okay? So the questions throughout this exam were a way that would guide you through the necessary steps in order to get the results from the very first one to the last, okay? Let's see what those results should be then. For a start, let's think about the free body diagram. How would the free body diagram for this beam should look like? So the free body diagram should show all the reactions as well as the externally applied loads onto a structure. So in this case, we're talking a beam. I may be able to draw it right here. Not sure if, yes. So I have this force P, which is 12 KIP per problem statement, and then I have the reactions right here, A, Y, A, X, and BY. I don't have any BX because it's a roller support, and I don't have a reaction along the horizontal direction or X direction in this case. Now, if you want to make it better, I mean, this is the bare bone free body diagram, and if you want to add more to it, you may want to specify this distance. So for example, this is 6 feet. If you could read my handwriting, but that's what I meant. The distance between the forces and some reference point. That would be beneficial, that would be helpful. But as far as the free body diagram, this is all that you needed to draw. All right, why is the free body diagram important? Because in the next step, we need to calculate the reactions at the supports. If you don't draw the free body diagram, you won't be able to get the results for the next part. Why? Because how would you determine the reactions? Let's just see. All right, let's start with the easiest one here. The reaction at point A along the X direction, because there are no forces along the X direction, externally applied forces along the X direction, then AX should be equal to 0. So balance of forces along the X direction, I'm not going to write down the equation for it. You guys, almost everyone got the correct answer for this one, so I don't think it's necessary to spend more time. So balance of forces along the X direction, that would give you AX is equal to 0. All right, how would you obtain the reaction forces at A and B along the Y direction? So you could take the, for example, I mean, if you want to write the equation for balance of forces along the Y direction, that's all right. but that's only one equation, right? We have two unknowns, AY and BY, but in this case, we only have one equation if you establish the balance of forces along the Y direction. We need one more equation here, right? What is that one more equation? So for example, the balance of moments around point A, or the balance of moments around point B, where you can find either AY or BY, right? And if you do that, and again, I'm not going to get into the details. This is the static. This is still the statics part of this exam. So AY and BY. So do you guys know what those are? If you have 12 KIP as the P, then this is somehow, it's like a fraction problem or a proportion problem. In general, let me just give you as a rule of thumb, when you're closer to the load as far as the reaction, then the reaction is going to be larger. So 8 KIP and 4 KIP are at the reactions that we were looking for. All right, with those reactions known, we are ready to take the next step. What is the next step? The next step is to draw the shear force and bending moment diagrams. All right, let's start with the shear force, which is the easiest one out of the two. So you just need to segmentize your beam into appropriate or pieces, and then determine the internal shear force in each segment accordingly. In this case, we only need two segments, right? Because we have two segments of uniform shear force. Those segments being AC and the other is CB. So pretty much one segment from the left support to the point where the load is being applied, and another segment from the point of load application, which is point C, to the right support, which is point B, right? How would you draw the shear force in this case? So you just need to cut a section in between the 2 points of the 2 ends of the segment and determine the internal force or the internal load, in this case, the internal shear force, for either the right piece of the section or the left piece of this section. So let's just draw the free body diagram for example, the left piece here. So I'm drawing the free body diagram here, and I have this reaction force of 8 KIP, sorry. And then I have these internal V, N, and M here. What would be the value for the internal shear force? You can establish the balance of forces, right, along the Y direction, and then determine V in this case. So V would be 8. Is it negative or positive? Based on the presumed direction, positive direction for V, this would be a positive V, right? And what you see over here is pretty much the tabulated values for the same diagram that we are discussing. You did not need to tabulate it this way. I'm just using this just to make the drawing, to make it easier to draw these diagrams in Excel. That's all. That's what. And any hand drawing would be also acceptable, so no worries there. Now, if you take a look at the right segment, the segment CB, and you just, let me see if I can draw right here as well. And again, cut a section and then use the right piece now. I have 4 KIP here, and then the shear force right here, and M. I established the balance of forces along the Y direction, and this time around, I'm going to get a -4 KIP over the segment CB, or in the segment CB. And what you see over here is that same concept here. The shear force with the appropriate units, KIP, and this is per length, and this is absolutely right. From point A to point C is 6 feet, and that's exactly what you see over here in the diagram. Positive 8 KIP, whereas over the rest of the length, it would be negative 4 KIP, right? How do you draw a bending moment diagram for the very same beam? So this is again something that we talked about it in class before the exam. Also, this is a statics thing. Just both of these diagrams are topics covered in statics. In order to draw the bending moment diagram, you need to determine the values at the reaction, the values at the supports y, because these would be our starting points. Okay. You can think of the shear force diagram as the derivative of the bending moment diagram, and at the bending moment, in order to determine the bending moment diagram, we know that at the two supports B and A, we don't have any reaction moments. Why? Because a roller support and a pin support would not be able to provide that. So we know that these 2 points are already zeros. We already know before we do any further calculations. And in order to determine the rest of the diagram, we can benefit. I mean, there are so many ways. I'm not saying this is the only way that it is possible to get the moment diagram from, the one that I'm going to explain to you. But this is an easy way. Just take a look at the shear force. This is the derivative of the bending moment diagram, which means that for the segment AC, I'm talking a curve whose slope is uniform. It has a positive uniform slope of magnitude 8 KIP. What would that be? A line, right? A line that goes up with a positive slope. So I need to go up, and then over the other segment, again, I'm talking a line because its slope is constant and it's a negative one, but it goes down, right? So I know that this goes up and then goes down. I just need to determine one additional point from this diagram in order to complete my calculations, and that's the point where the transition from the negative slope to the positive slope happens. Where is that transition happening? Exactly where this step happens. And this is exactly at the point where the load is being applied. So what's the magnitude of it? You can use different methods. The easiest of which would be cutting a section exactly where this load P is being applied. So let's just do that now. I have 8 KIP, which is being used here. And then I have this distance, which is 6 FT per diagram, 6 feet. And then I have this normal force, I have this shear force, and then I have the bending moment. And there's nothing else. And again, what is it that I'm trying to obtain here? I just cut a section right at where the point C is, and I'm drawing the free body diagram for this entire thing. Now, is it easy to calculate the bending moment, or M here, in this free body diagram or not? You establish a balance of moments in this free body diagram, and there's this 8 times 6 KIPFT moment, which is going to be balanced off by M. So M is a positive value, and this is going to give you 8 times 6 KIPFT, which is 48, obviously, and this is exactly what you see over here. So this is 48, and our diagrams are complete now. All right, why do we need to draw these diagrams? Because we need to determine the stresses, okay? In this particular case, this was actually a little bit of piece of, educational piece where the purpose was just to see if you guys can track the variation of the forces and bending moments along the length of the beam. But in general, we draw these diagrams in order to determine where they become a maximum or minimum, the shear force and the bending moment values, the internal shear force and bending moment values. Also, we may be interested in knowing the values for these, for the stresses and as a result for these internal loads at a particular point. What is that particular point in this case? The particular point is this section, the section NN, which is positioned 9 feet away from either end. All right, so we are interested in that particular section, and as a first step, we need to determine what the loads are at that particular section. What are the loads? Obviously, at section NN, where N is equal to 9, and that has been highlighted in yellow here, the values for the shear force and bending moment diagrams, the shear force and bending moment are not the maximum values. They're rather to obtain from the diagram. So for example, 9, we're here, and this has been marked up. So your bending moment is 36, whereas your shear force is negative 4,000 pounds or negative 4 KIP. So these are those values that we need to use for the rest of our calculations. All right, but before we do that, this is some part of the information that comes, but keep in mind that we need to calculate the bending stresses as well as the shear, the transverse shear stresses, right? So if you start with the bending stresses, negative my over I, m, which is being determined based on this diagram, and this is the value for it, is only one variable out of 3 that we need to know, right? You also need to determine I and Y. Okay, I and Y are being determined based on the cross-section. Do we have that cross-section? The answer is yes, it's right here. To determine both of these parameters, I and Y, we need to determine the centroid of this cross-section. How do we determine the centroid of the cross-section? So this is the method that is used or was used in statics, and we're gonna just stick with it. It's not a big deal. And we're just using the same tabulated approach towards this. First, you need to divide up a composite area, as it was named in statics, into several sub-areas whose geometry is much easier to be used for the purpose of the calculations. And in this case, you may have divided up this unsymmetric flange section into 3 sub-areas: the top flange, the bottom flange, and the web. So in order to save time and not take too much time, I'm just showing you the tabulated values. So we need to determine the Y for the centroid at each sub-area, and then multiply that by the area for that particular sub-area and add them up, and then divide them by the area for the entire cross-section, right? And if you do that, then your centroid, the Y position for your centroid would be equal to 8.625 inches, measured from the bottom layer, from the very bottom of the cross-section. So we still don't know Y, we still don't know I, we just know what the centroid is. How do we determine Y in general when we determine the position of the centroid? Keep in mind that Y is the distance between the centroid, or where this is exactly where the neutral axis is positioned, the distance between the neutral axis and the point of interest. So we have two such points in this case. One is point F, the other one is point E. And these have been marked up in the figure. And as a result, we can determine both now that we know exactly where the centroid is positioned or the neutral axis is positioned. So Y could be determined easily. How about I? I needs a little bit of more work. We need to use that parallel axis theorem again, coming from statics. So again, we're going to use the same tabulated approach towards this. We just need to divide up an area, a composite area, into several subareas, for each of which we need to calculate the moment of inertia around its own neutral axis. And then add to it one additional term, which is comprised of A, which is the area for the sub-area, multiplied by D squared, D being the distance between the neutral axis for the sub-area and the neutral axis for the entire section. And if you do that, then you're going to get this. This would be the moment of inertia for the entire cross-section. Okay, so we do this around which axis? Around the neutral axis, and the neutral axis is the direction for the neutral axis. If you take a look at this section, would it be like this or vertical to it? It depends on the direction for the load, and based on the given load direction, then this would be the neutral axis. And there's no other way that you could give it a different direction for the purpose of these calculations. All right. I'm going to go over the rest of the solution process, if you guys could bear with me a few more minutes. And I'm going to get back to you to see if you guys have any questions or any unclear points here. Now, we're going to go back to this equation for the purpose of calculating the bending stresses. But keep in mind that we have points of interest, point E and point F, each of which has its own position, which is obviously clearly marked up in the figure. One is located at a junction or the overlapping edge or the shared edge between the flange and the top flange and the web. The other is just at the topmost layer of the cross section. All right, so over here, this is just the pure calculation of those stresses. One thing before we talk about the numbers. I specifically asked about, on the exam, about the state of stress at those 2 points, compression or tension, because these points are both above the neutral axis. They should be, as a result, both under compression. So this is as far as that. As far as the calculations, so that you can obtain the values for the stresses, I would suggest that you be consistent as far as the units, all right? And this is what I mean. When you draw the shear force and bending moment diagrams, you would use the units of convenience, I would say. And it's absolutely all right, because we don't really care for, we don't want to get stuck with the numbers there. The overall trend and just some appropriate units would be all right. But when you want to calculate the stresses, then this is where the consistency matters most. So for example, what I did in case of bending stresses at points E and F, I used the value for the bending moment in pounds, inches, not the KIPFT. Why? Because my other values, such as Y and I, are both in inches. And it would be easier for me to convert the forces into, or the load, the bending moment, into pound inches, so that everything is going to end up with pounds per inches squared, which is the PSI. In which case, I'm going to get the two values that I'm just showing to you right here. Obviously, we get negative stresses, but then keep in mind that the stress at point F should for sure be larger in magnitude than the stress at point E. Why? Because it's farther away from the neutral axis. Right, so we're not done yet with the bending stresses. So these were the two bending stresses. There's one additional bending stress that we need to calculate. It just says the maximum tensile stress in the part, right? At that section. So how do you determine that? Keep in mind that the areas atop the neutral axis are all under compression. So we have to think about the bottommost layer in that section to obtain the maximum tensile stress, right? And for that particular case, then the moment of inertia would be, the area of moment of inertia would be the same over the section, the one that you use, the same one that we use for calculating the stresses at points E and F. The bending moment would also be the same because that's the same for the entire cross section. The only difference would be the value for Y. So that's from the neutral axis to the bottommost layer, which is equal to this. You see, you're going this way from bottom, from the neutral axis to the bottom. So that's equal because we measured the position of the centroid from the very bottom layer. Then as a result, the value for it would be this. So that's what you see over here. And overall, we get a positive stress of the magnitude that you see over here. 3,000 something PSI. Okay, so this is as far as the bending stresses. Now let's move on to the transverse shear stresses. The values for both points have been asked for, but one of which was actually super easy. We already knew it before we did any of these calculations. The shear stress, the transverse shear stress at point F should essentially be equal to 0. Why? Because that's the topmost layer. And the topmost layer and the topmost layer, the Q is equal to 0. Q is the first moment of inertia for the points that belong to any section of the cross section. And that's essentially the area atop that, the thickness line that that point belongs to, multiplied by the distance for the neutral axis for that area, that sub-area, and the neutral axis for the entire cross-section. And for the case of point F, obviously it's equal to 0. Now let's talk about point E. Q is shown over here. I is going to be the same as the I for the cross-section that we use for the purpose of calculating bending stresses. T is the thickness line. Is the thickness of the thickness line because point E is shared in between the flange and the web. Then we have to determine which thickness are we talking, the flange thickness or the web thickness. So the problem statement specifies that. It says it belongs to the thinner section, which means it's part of the web, not the flange. And V in this case, V is the internal shear force. Again, where do you get it from? From the shear force diagram. And the value for it is provided here. And then once you do the calculations, then this is what you're going to get for the shear stress. So let's just write down the equation for tau is equal to VQIT. And this is these are the inputs to this equation, and this is the final answer for it.